Good afternoon all. My name is Kilomo Matsivadondro, and I'm going to present my thesis project work entitled Binary Based Error Correcting Codes Based on Properties of Cycle and Parity Check Matrix. But before I proceed, I wish to thank my thesis supervisor, Dr. Sinavavi and Dr. Awin Chan, and my thesis coordinator, Ms. Mayam Jonkman, for their sterling support and guidance throughout the thesis project work this past semester. I will briefly run through the contents of the project thesis work, which are shown on this slide. Introduction, motivation, aims of the project work, codes for the correcting base errors. Yes, there are codes for correcting base errors, but are very inefficient and do not scale up to the challenges imposed by base errors. Development of algorithm, determination of cycle and parity check polynomials or checks, and n values. I will elaborate what hx and n values are in a short while. Conclusions, and that will lead us to future endeavors on the thesis project work. This is basically a block diagram of a general communication system. Of noteworthy is the interleaver and the de-interleaver, which in my thesis project work are replaced by the computer search. Motivation for the thesis. Although the importance of base errors in terms of the degree or extent of impact on transmission systems cannot be overemphasized, very little research in the field of error coding designed to find codes that effectively correct base errors has been undertaken. Base errors are among the most important types of channel errors because their effect spreads over a sequence of symbols. Obviously, it is easier to design and implement random bit errors correction codes than base errors. Why? Because a code will have the maximum base error correcting capability if the allocated length for the correction of base errors is set greater than the length of the error patterns. And therein lies the challenge. So, research, as I've said, have not been forthcoming, so it's an under-researched field for detection. Why? Because it is difficult to design a code that will detect and correct in the first and second instances chunks of binary bits that have been either wiped out completely or drastically negatively impacted due to base errors. So, the aims of the thesis of this project work are as shown on this slide, and I'll briefly outline. Derive or find codes, these are binary codes, circulant, with maximum base error correcting capability, and investigate the properties of cycle and parity check matrix in order to attain thesis project goals. And of utmost significance is that codes sought after should have rates greater than 0.28. So the rate is nothing but a ratio of the number of intelligent bits, that's bearing information, which is k, divided by the number of total bits transmitted per block, which is n. Why this is important is because lower rates, the bottom line is we would be wasting satellite bandwidth, as in the case of the United Nations, by due or to the geographical sparse nature of the missions. We rely heavily on the VSAT, and I can tell you satellite bandwidth is very expensive. So we just have a brief look at codes for correcting base errors, as shown here. Linear block codes. They're designed to correct a number of bits within a specific length. Reed-Solomon, they are non-binary, disadvantaged in their decoding complexity. However, they are employed, like I said, in the United Nations network systems for VSAT and terrestrial microwave networks. Low density parity check codes, good but ineffective in dealing with base decodes, because low density parity checks have problems with implementation where large or sparse codes are implemented. Fire codes, they are binary base error correcting codes which are not efficient in random error correction and in also base error correction. PCH codes, efficient but also not scale up to the best challenges. Second parity check matrix based cyclic codes. Well, this is the type of codes that this project work focuses and investigates in order to obtain optimal base error correcting codes, also with a high performance on random error correction. So this project work aims at improving on the predecessor research work, which has shown that optimal base error correcting codes with a high performance in random error correction as well could be achieved either with interleaving or computer search. Developing an algorithm of optimum base error correcting cyclic codes is based on parity check polynomials, as I've outlined. Computer search gives the number of binary cyclic codes with rates between 0.28 and 0.47. And these cyclic codes have shown minimum weight, which renders them capable of correcting random errors too. Therefore, multiple base errors and random errors could be corrected when new schemes of cyclic products codes derived from circulant cyclic codes are employed. Now, circulant codes optimum capability are shown by the Rega bound equations shown in this slide, and the following equation, which shows the circulant parity check matrix equation, which actually will be employed by the thesis project work. I just want to highlight the fact that a circulant parity check matrix can be divided into two parts. The first part, which is n minus x by n submatrix, and bearing n minus k minus 1 cyclic shifts, and the second submatrix, which is a k by n submatrix, which is the one actually shown in this slide. Now I'll introduce the notion of zero span, which is the maximum number of zeros components between two ones, and this normally is an n minus k minus 1, because the last n minus k minus 1 zeros of the first row of the submatrix determines the maximum zero span. So basically in this submatrix here, I've shown nz1, nz2, nz3 corresponding to submatrices of the second submatrix, which is submatrix 1, submatrix 2, submatrix 3, and submatrix 4 respectively. I've also shown the columns here, which are colored in orange, yellow, gray, and brown. This actually aids in the ultimate determination of the maximum zero span, which in this project we will use to determine the total number of different codes that we can come up with. So this submatrix and the first submatrix will give the ultimate maximum zero span. For instance, if that is k, then it means we have 2 to the power k different conditions or different codes, and we will therefore develop a MATLAB script that will compute hx and corresponding n values. It's of noteworthy to note that all codes may not be relevant to our algorithm. So this slide here shows the hx cyclic parity check matrix corresponding n values, and that these two values will be stored in different files, which is basically shown on this slide and on the next slide. Now, in conclusions, simply want to share with you that from the thesis work project thus far executed, it can be concluded that it is possible to find cyclic parity check cyclic codes with high or maximum base error correcting capability to outperform currently employed for base error correction. Some codes thus found will be used to correct random errors as well, and would surely outperform current random error correction codes. Which leads us to the future endeavors. Work will be advanced, and parity check matrix codes obtained and their corresponding n values by employing computer search for improving efficiency of the codes. And now these codes will be used in correcting base errors in transmission and storage media. And these codes also, as I've said before, will outperform the current codes being used. And with that, we come to the end of this presentation on binary based error correcting codes based on properties of cyclic parity check matrix. Thank you.